everybody. Welcome to OpenCV Weekly Webinar. I'm Satya Mallick, and today I'm going to talk about You Look Only Once, YOLO Object Detector. And with me is Phil Nelson, who is the content manager at OpenCV.org. Hi, Phil.
Good morning, Satya, and good morning, everybody else. Welcome back to OpenCV Weekly Webinar. One of the things we do on this show is Q&A from you in the audience. Please use the Zoom Q&A functionality at any time during the show, and we'll try to work your questions into the flow of conversation. Also, we're going to do a special giveaway at the end of the episode, and it's a brand new thing. You want to tell them about it, Satya?
Yes, it's a brand new thing, and it is very much tied to my announcement today. So we are going to launch a Kickstarter campaign. Yes, again, we are going to launch a Kickstarter campaign on Valentine's Day for all the people who are in love with deep learning and AI. So we are creating a new course called Deep Learning with TensorFlow and Keras. We've been working on this for quite some time, and this week, or actually next week, Monday, we are launching a Kickstarter campaign for this course. It will be a little over a month. And it's it's going to be an exciting Kickstarter campaign. If you are interested in a career in computer vision and AI, very interested in deep learning, then this is a solid course to start. There are no prerequisites for the course, so please join us, get to be notified at opencv.org/Kickstarter. Let me repeat it, opencv.org/Kickstarter. So yeah, I mean, anybody who's interested, it's I recently read that the word love in tennis, when you're at zero, they say love. And I was wondering where that comes from. It comes from encouraging people, that people who are at zero, who have not started yet, they are doing it for the love of the passion for the sport, right? So that's why we decided, okay, let's do it on Valentine's Day, for people who are starting at zero, who are passionate about, for the love of AI, right? So who are passionate about AI, have been thinking about getting started, or even are amateurs in AI. There are a lot of people who have sort of knowledge about AI, but they cannot face a job interview. This course would be very good for those people also. And the word amateur also has its root in the word love. Amateur, also the word, I think it comes from the Latin word amare, which means love. So you're an amateur is a person who does things for the love of doing it. So interesting nuggets for Valentine's Day.
I did not know that. I learned something already this morning. I'm
just
calling it a day.
Okay. So let's get started. The main thing. The person who wins the giveaway this for this session would win obviously deep learning with TensorFlow and Keras. And we still have a few days for this campaign to go, and we are trying our best that as part of the campaign, we also give away this book by Francois Cholet. This book is going to be the companion book. We recommend this book, although the course doesn't need any book. It is self-contained, but if you have to buy a book, you should buy this one. And if you're going to back our course, this book would be given to you for free. We are trying our best. Hopefully it will be done. Let's see.
It's a big old book. I mean,
I love this book. Very well written, not just from a technical point of view, which is obviously good. Francois Cholet is the author of Keras, but also from love reading some books, right? It's not like boring technical thing one after the other. There is some context there. So I really like the book. Okay. So let's get started. We have another announcement at the end of the webinar as well. And we'll also ask the question at about the 50-minute mark.
Yeah, blockbuster episode here on OpenCV Weekly Webinar, folks.
Okay, so this is the second part of our series, which was you only look once. And I will just quickly recap so that people have
Yeah, we
not
had a
used
bit of a
PowerPoint in
history
a
of
long
this.
time. I don't know how to go to presentation. It used to be somewhere here.
Man, beats the heck out of me.
Okay, right here.
There we go.
Okay. Oh God, it's worse
Yeah,
than
it's
what I.
doing speaker mode. Computers, everybody. Were they a mistake? It's impossible to know.
Okay, I'll just stick with this.
Yeah.
Okay, so last time we decided that we went through YOLO V1 and YOLO V2. And I just want to quickly recap what we went through. YOLO is basically a very simple convolutional architecture. And YOLO, the way it is trained is that you divide the image into these cells, and each cell was responsible for predicting two bounding boxes. And the confidence was actually the confidence. It also showed what is the confidence of an object in that bounding box, right? And we know that, using this mechanism, because there are it's a 7x7 grid, and there are only two bounding boxes predicted per cell. So the total number of items we could get is only 98. So very small number of bounding boxes. And, we also went over the training mechanism of how these bounding boxes um, uh, are selected, etc. So each cell was responsible for selecting the bounding box around the object. And, we created a loss function, which basically was a combination of classification as well as detection. So here, the box is also responsible for predicting what is the class of the object, right? So the cell actually predicts what is the bounding box, as well as what is the class inside that bounding box. And if the confidence of the bounding box was low, the class did not matter, right? So that was YOLO 1. As you can imagine that, once it was trained and it was run, you could find many bounding boxes which were combined using non-maximum suppression, or actually filtered using non-maximum suppression. So, things like that, you ended up with getting this. The problem, obviously, we went with this. What was the reason? What is the problem with this kind of approach with YOLO V1? The very first thing was we had this quiz question. Let's go over the quiz question. These are all, yeah. So the problem was that it could only detect 98, a maximum of 98, not even 98, actually a maximum of 49, I think, objects, but not even in a row, right? If there are more than 7 or 8 in a row, more than 7 in a row, then it would not even detect those. So that was a question. Then came YOLO V2. YOLO V2 is also called YOLO 9000. YOLO V2 is actually the model, and YOLO 9000 is the object detection system, but most people just call it YOLO V2. The reason YOLO 9000 is important because the paper name is YOLO 9000. So if you actually want to look for the paper, better look for YOLO 9000. It will be easier for you. So there were a bunch of ideas in that improved the accuracy of YOLO V1. So the very first thing they did, let's actually go to another slide here. So these are the various things that were done to YOLO V1 to get to YOLO V2. Now, this is an amazing slide, and I really I'm glad that Joseph Redmond, who is the primary author of YOLO, included this. It tells us that when some progress is made, there are things that we don't know in the beginning what things will work out, and it is incremental. So even though it is called YOLO V2, you can look at the versions. There are so many versions of YOLO before they reached YOLO V2. And each one, they were changing one or maybe two things at a time to improve the model, right? So the first thing they did was a batch normalization. This is a training technique that it's pretty much very standard training technique. Whenever you have convolutional layers, you should be doing batch normalization. And when YOLO V1 came out, that was not an established technique, right? So just adding this, you can see that they got about 2.4% improvement in map. So then they used a high resolution classifier. The resolution of the box that they were using earlier was 7 by 7. Just by using a feature map which was bigger, they could get some additional improvement. You can see that this is a big improvement. And that's obvious, right? Earlier we were restricted by only 98 boxes. And now you could go to 13 by 13 was the feature map they were using. And they were using 5 boxes inside it. So 13 times 13 times 5, somebody help me out. Whatever it is, 845, right? I may be off, but that's fine. Some 800 something. Yeah, so you could see that with that, they improved to 69.5. They also tried this idea of using anchor boxes, which was a slightly different concept. Earlier, what used to be in YOLO V1, the boxes were predicted directly. So X, Y, width, and height coordinates were predicted directly by the system. But in this new architecture, what they did was they had this concept of anchor boxes, which means that they had some predefined shapes and sizes for the boxes for each cell. And the architecture was designed in such a way that only the offsets from those boxes were calculated. Now, this is science. All the good ideas don't always work out. So when they actually implemented anchor boxes, the map decreased. You can see here, 69.5, it decreased to 69.2. And you can see that in the row that corresponds to anchor boxes, they dropped the idea of anchor boxes in subsequent iterations. However, I actually spent half an hour arguing with my team yesterday whether they actually dropped it or not. And if you look at all the implementations of YOLO V2, anchor boxes are there. They are not removed like this. But if you look at this table, anchor boxes are not there, right, in YOLO V2. But in all implementations of YOLO V2 I've seen, anchor boxes are present. And they do reduce the map slightly, but they also increase the recall value by about 7%. It is also there in YOLO V3. So, this was not, after all, a bad idea. They still preserved it. The other change they made was that they used a different network. The different network, if you look at this, you can see that the different network did not change the accuracy. The map did not change with a different network. What did they gain with this different network? Speed. YOLO V2 was they called it. It was stronger, faster, better, faster, and stronger. Those were the three terms they used.
From that Daft Punk song.
Right.
Higher, better, faster, stronger.
Right. So so for the faster part, it is funny that YOLO V1 actually used a bigger network. The number of parameters in the network were bigger. It was based on a modification of GoogleNet, and YOLO V2 was based on DarkNet 19, which had 19 convolutional layers. The earlier version, the GoogleNet version that they were using, it had about 24 layers. So by just removing, making the network smaller, they were able to make it faster. So even though you can see that the new network did not improve the accuracy substantially, it increased the speed by 30%. So that was a big deal. We also learned that they used dimension priors. They used k-mean clustering to find what should be the dimensions of these anchor boxes, right? And they found out that there are certain dimensions based on the training data, certain dimensions were preferred. And because you're choosing those dimensions, the training becomes easier. You're more likely to be closer to one of those dimensions, the predicted boxes. So, okay, so then you get some more improvement. And then you can see that gradually you have these other things also. For example, they have this pass-through layer where they were, so in the pass-through layer, what they were doing is you had a low resolution feature, but from some other layer, they were taking high resolution features also and combining these two feature maps to create additional information at the time of detection. So basically using, it's almost like a multi-scale kind of thing. So yeah, and then they finally used a high resolution detector as well, which means that, the 13 by 13, etc. So doing all these things, one after the other, they were able to get, from 63.4, they were able to increase the map on VOC data set to 78.6. And the reason I really like this table is it presents us with this is exactly how research should be done. You change one thing at a time, see what effect it has, and then keep going gradually, keep adding on to it. Don't try to change a lot of things at the same time. Otherwise, you will be confounded what exactly, even if they are good ideas, you don't know whether they will work or not. As you can see that anchor boxes did not quite work, at least in this version. So, and it also shows that, there is a lot that goes, all the little things, they add up to create a network. And all this is experimentation, right? It is, you can come up with many good ideas, but only some of those ideas will work. Nothing is obvious. Some maybe batch normalization and things like that were obvious, but a lot of things are not obvious. You have to do experimentation to figure out. And the second thing I want to emphasize is that this is, if you look at YOLO V2 paper, it is a collection of borrowed ideas, right? And there is nothing wrong with it. You should be proud of stealing from other people in research, because that's the whole point of collaboration, that we come together, steal from each other, and make our things better. I mean, if you look at TensorFlow versus PyTorch, that's exactly what is happening. All the good ideas from TensorFlow are making it into PyTorch, and PyTorch good ideas are going into TensorFlow.
It's a cliche for a reason that, if you want to go fast, go alone. If you want to go far, go together.
Right, right. So I love this, from V1 to V2 transition, they picked all the good ideas that were present in the community and tried pretty much all of them, and they got this massive improvement, right? So now let's come to YOLO V3. YOLO V3 paper, sorry, I did not add a link to the paper, but if you do YOLO V3, you'll find it. This is a technical paper. You can see how it starts though, right? It says sometimes you just kind of phone it in for a year. I didn't do a whole lot of research this year, spent a lot of time on Twitter, played around with GANs a little. This is the YOLO V3 paper. It sets the tone for the rest of the paper. It's very interesting. One of the things I really like about the paper is at the end, they also explain what are the things that did not work. And that's very important, because it helps people not stumble on the same mistakes that they have made or the things that did not work out. Even if people want to try it again, they will at least have a word of caution from them that, okay, we tried it and it did not work. So it saves a lot of time for people. And this particular paper is also very approachable in the sense that it's written in plain English in a fun way, and definitely worth a read. So what was the motivation for YOLO V3? YOLO V2's motivation was that it had to be better, faster, and stronger. all three of them. But what happened was YOLO v2 was not as accurate as the state-of-the-art algorithms at that time, architectures at that time. It was blazingly fast. Phil, do you want to ask me any math question? I'll answer it in, quick.
I'm so bad at math. I don't actually have any math questions.
Any math question, e to the power something, just make up something.
Pi times 4.
Yeah, 42 is the answer. See, I was blazingly fast,
Bingo.
but I didn't say accurate, right?
You got it.
So fast is not enough, right? It has to be accurate. And YOLO v3 tries to fix that problem. It is better. It is not faster than YOLO v2. And it has many other good qualities, right? So that was the motivation, which was slightly different from the motivation earlier. Although it was not faster than YOLO v2, it is still much faster than other state-of-the-art algorithms at that time, right? Let me show you this this chart. This chart is included in the YOLO v3 paper, and you can see that on the x-axis we have the inference speed. How much time it takes. Let's look at RetinaNet, for example, right? Something that takes 90 milliseconds. It means that it is doing only about 10 frames a second, 11 frames a second. So you cannot, for anything that that needs to go on a vehicle or something like that, you need at least 30 frames a second, maybe 60 frames a second. So this is not enough, even though it is accurate, but speed does count a lot in object detection, right? So YOLO v3 is on this side. It's I also like, I don't know whether this was done intentionally, but I like how it is represented. They took the graph from a previous paper, and they just slapped their data onto this.
It's literally off the chart.
Exactly. See, they want, I think this was done intentionally, right? They just wanted to show that our results are
Pretty
off
funny.
the chart. Yeah, so YOLO v3 was more accurate, faster, not more accurate than the top in the game, but it was more accurate, more accurate than YOLO v2, but also much faster than other detectors. In general, YOLO has focused on speed. So that is something to keep in mind while choosing this detector. So what are the good things about YOLO v3? First of all, it works on larger resolution image. This is obvious, you have more information, so you are going to be better at predicting. It uses more bounding boxes, and we'll see, how many more bounding boxes. It uses a larger model. YOLO v2 used the darknet 19, which had 19 convolutional layers, and that was not enough for a good accuracy. So they came up with another architecture. It had 53 convolutional layers, and it is called darknet 53. So it's using a larger model. When you use a larger model, a deeper model like this, the accuracy improves, right? It is very well known that deeper models can learn much accurate. They tend to be much more accurate than shallower models. The challenge becomes as the depth goes, as you keep going deeper and deeper, it becomes difficult to train because of some problems like vanishing gradient, etc. So the other thing was multi-scale inference. So earlier, if you remember, YOLO v1 was doing inference on a 7x7 feature map. Ultimately, after passing through all these convolutional layers, the feature map we are getting was 7x7. And in YOLO v2, the feature map was 13x13. So it was bigger, but it was still 13x13. In YOLO v3, they are doing inference on 3 different feature maps. The first one is 13x13, the second one is 26x26, and the third one is 52x52. So you can see that it is actually doing it at multiple scale. Now, if you remember, in YOLO v2, the training was done at multiple scale. We had actually created multiple sizes of the input image, and we had trained this using multiple, at multiple scale, but we had not done inference, which is, the prediction part was not done at multiple scale. So slightly different. In YOLO v3, we do both training, where we use multiple images, multiple resolutions to do this. But also the inference is done on this feature map of multiple sizes. So you get many more boxes. They also changed the loss function slightly. That's a smaller detail. But the main difference between YOLO v2 and YOLO v3 were two. Basically, you could say that they used a larger model, so it was more accurate. And the second thing was this multi-scale inference, where the feature maps, there were 3 different feature maps on which inference was being done. Okay, yeah, slightly better. Okay, so now we are ready to have a question actually. So first, let me explain this table, and then we have our question. So YOLO, the input image size for YOLO was 224 by 224. As I had already said, that it used a network which had 24 convolutional layers. The feature map which was produced at the end was 7 by 7, and the number of bounding boxes total was 98. That is 7 times 7 times 2. So there were 2 bounding boxes predicted per cell. YOLO v2, the input size was 416 by 416. They used a different architecture, which is darknet 19 with 19 layers. And that is why you can see that the number of layers dropped substantially. And that's why the speed went up. The feature map was 13 by 13. And so the total number, oh, I got that thing right. So the, the number of bounding boxes was 13 times 13 times 5, because there were 5 bounding boxes per cell. Okay, so 845 boxes. Now YOLO, YOLO v3 comes in many different flavors, but the most promising or the most accurate flavor uses the input image size of 608 by 608. There are 53 convolutional layers in the main feature extractor. And the feature map is multi-scale, right? It uses 3 different feature maps to do its inference. And for every scale, it has 3, what do you call it? Bounding boxes. Now the question is, what is the total number of bounding boxes? And you just cannot give me the answer, because I think you can Google the answer. You have to tell me, you have to write out the expression, like I have written down the expression here. You have to write out the expression. So this is the quiz question that would earn you deep learning with TensorFlow and Keras. What is the total number of bounding boxes?
And please only answer in the Zoom chat, not LinkedIn and whatnot. Can't monitor those in real time. Sorry, folks. You have to give the expression. Okay, so we do the actual expression of what it would be in order to win on this one. And the final result, of course.
Okay, let me check if we got. All right, I think we got the right answer. The right answer is, Phil, I'll let you pick the winner, because I don't know who's the who said it first.
Yeah,
but the answer is 13 times 13 plus 26 times 26 plus 52 times 52, whole thing multiplied by 3, because there were 3. So
which
we have
1,000 or 10,000.
No, 10,000 something.
Yeah.
What is it?
10,647.
Yeah. So that's the answer. So those were that many boxes. You can see that there are more than 10 times the number of boxes in YOLO v3.
Big Big
Okay.
difference.
Yeah.
Yeah, I'll have to look at the chat here on
Okay.
the scroll back later, but I'll reach out to our winner after the show.
Yeah. Yeah. And even if, the final answer, as long as the expression is right, that should count.
Yeah, I agree.
Okay. Now let's look at the variants of YOLO. YOLO V3 comes in 3 variants: YOLO V3 Tiny, YOLO V3, which is the standard one, and YOLO V3 SPP. SPP stands for Spatial Pyramid Pooling. Don't worry about what exactly it means right now. It just means that it is it is large. So the tiny version is not very tiny. I mean, it's called tiny, but it's not like you can easily use it in an edge device. So be careful about that, when you're using tiny version of YOLO. It is the fastest member in the family, but it still requires GPU for real-time performance. And it is based on a modified version of darknet 53. YOLO V3 is the standard one, and YOLO V3 SPP is an even larger but more accurate model, but slower than the other two. Now, so this was YOLO, and YOLO was developed until YOLO V3. It was developed using darknet, and darknet is a framework just like PyTorch and TensorFlow. Darknet is a framework written in pure C, right? I don't know how many people use it. Everybody who uses darknet is for training YOLO. That was the primary reason for using darknet. But I think there could be some applications where you need very high performance and you need native C, not even C++. In that case, people must be using darknet. I just don't know enough about that space. Who are the people using darknet? So obviously, YOLO was so popular that people started making versions of YOLO, which were in other frameworks. And the most popular one was V3, YOLO, a PyTorch version of YOLO V3. And this is actually where YOLO V5 was also born. So somebody created, Ultralytics actually was heavily involved in YOLO V3 PyTorch version. And they created this YOLO V5 from this branch YOLO V3. And if you look at the architecture, no, actually, if you look at all the training scripts, the model blocks, etc., the code is almost identical to YOLO V3. And there is no paper explaining what is YOLO V5. So you literally have to dig into the code to figure out, what is different and what is not. So we did that, and we found that most of the thing is the same. Utility scripts, etc., is the same. What is different is the model architecture. There are many different flavors, and we'll go over it in the next slide. This architecture is based on it's not based on darknet 53. It is another one. It's a variant of a bottleneck network. It's skipping. I cannot remember it right now, but it's a different architecture. And then the anchor box, if you remember, we were using in YOLO V3 and V2, the anchor boxes were determined using k-means clustering. And here, the anchor boxes are determined using some genetic algorithm. And frankly, I don't know, which one performs better and how much it performs better. One big difference between YOLO V5 variants and YOLO V3 variants is that YOLO V5 variants uses something called model scaling. So model scaling is this idea of changing the size of the model using a scaling factor for the depth of the network and the width of the network. Let me explain a little bit. As I had mentioned that if you add more layers to the network, it becomes more accurate, right? Because it can represent, the abstraction can be represented in multiple ways. So it just becomes more accurate. But at the same time, deeper networks are harder to train. So people also know that wider networks where, so deep networks basically means that the number of layers are more. Wide network means that the number of channels in their filters is more, right? So the
So would
yeah.
this also mean that you're more susceptible to like overfitting or underfitting your data with more layers too, or is it?
Yes, yes.
Yeah,
If you have very little data, you should not use a very deep network. Yeah.
that makes sense. And there's obviously there's going to be some performance cost as well. Is that, you know?
Yeah. You let me correct myself. You
Hmm.
can use very deep networks, but you should not train all the layers. You know, you use fine tuning, so you should not train all the networks. Maybe you use the network as is, the pre-trained model, and just fine tune the last layer or last two layers of the network, something like that, right? Um, wider networks means that the filters have more channels, and we also know that wider networks also produce better results. So, and we also know that if you increase the image resolution, the quality will improve, right? Because there is more information. So the question becomes, oh, should you go deep? Should you go wide? Or should you increase the image resolution? What should you do? So there is a paper called Efficient Net, and I have a blog post about it on learnopencv.com, which basically goes through it in a very systematic way, that they found a systematic way of model scaling. If you want fewer parameters, they came up with some optimal strategy, not optimal, but reasonably good strategy for scaling the model, so that you don't have to think like, uh, in
I
this
went
one.
ahead and dropped the link to that Learn OpenCV blog post in the chat here, by the way.
Thank you. So in YOLO, each one of this, YOLO v3 Tiny, YOLO v3, and YOLO v3 SPP, they are handcrafted networks. They are all slightly different variations. They are not scaled networks. But in YOLO v5, this thing, these models are scaled automatically. So you have these variations, and it is using some standard techniques that were developed with Efficient Net. There is some criticism of Efficient Net that these models are so highly optimized for ImageNet that they probably don't do a great job when you're doing transfer learning on other kinds of data, let's say medical data. People, I've not seen
Things that
people
aren't
use.
necessarily a part of
Yeah,
ImageNet.
yeah. So people, I've seen people use Inception v3 a lot in medical data, but they don't use Efficient Net, even though it gives very good results on ImageNet. So something to bear in mind. So now let's look at the variants of YOLO. So these are the various variants of YOLO v5, and it just goes, N is for nano, S stands for small, M is for medium, L for large, and X is for extra large. And it pretty much requires no explanation. It basically, they are all listed here. The number of parameters, the smallest model is just 2.5 megabytes. So that's the benefit, that you can use any one of these networks and run your training, right? So now let's get back to, this is the information that we have about YOLO v5. As you know, that this can keep changing. It's not like it's not a published paper or something like that. So the code can keep changing and new things could be added. But right now, this is the information we have about YOLO v5 looking at the code. So let's go over and see how to train a Snowman detector using YOLO v5. One thing I like about YOLO v5 is that, first of all, it is PyTorch based. And the second thing is that it is, makes things very easy for people to use. And we'll see that in this notebook.
Got to be more patient, Dan. They're getting restless in the chat. They're excited to see the super jazzed to see the collab notebook finally.
Right. Okay. So okay. So the notebook is actually very simple because YOLO v5 makes it very simple. But before we start, I actually think that people should use something called weights and biases setup. And what it does, it allows you to visualize your training in a very nice format. So the first thing you need to do is go and create an account on weights and biases. I have already created this account. Once you create this account, you go to settings, and inside settings, inside settings, you'll find the API key. So this API key, and it can be changed, so I'll change it after this webinar, but this API key you can copy, and we will see how we can actually
not displaying great operational security here.
It doesn't matter. I mean, sure, somebody will publish their model onto my account. Big deal. So yeah, so the API key you can actually copy from here. And this allows you to create very nice looking graphs. And I'll just show you the graph quickly so that, so this is the result of me running the training. And you can see that all the loss function is coming down. Everything is here. And it also stores the model for you. So very nice.
That's a lot of functionality that would be a pain to do by hand for sure.
Oh yeah, and if you look at this, this is all you need to do. These 3 lines. So when you do pip install W and B, weights and biases, W and B, I don't know whether it's visible. I just made it slightly bigger. Okay. And then import W and B, and then log in. When you log in, it will ask you for the API key. You put in the API key, and that's it. You don't have to do anything else because YOLO v5 will do everything for you to create that on your account. So when you run this, it will be on your account. So I was hoping that this thing would run in real time. The training would run in real time, but unfortunately, it still takes about 10-15 minutes on a GPU. So I have pre-done it. So let's go over it. First we set up, whether this is for training or inference. We say that training is true, and we set the number of epochs. So an epoch is when all the data passes through, the training data passes through training once, that is called 1 epoch. So we are saying that we are going to pass all the training data through our network for training 30 times because it's an iterative process. It is going to do that. YOLO v5, you simply git clone YOLO v5, you basically go into that account. And then we have this data set prepared for you. This data set, let me quickly what does the data look like? You're still able to see my screen, right?
Yep.
Okay.
See it.
So we have collected all these images of YOLO from the internet. Not YOLO, sorry, Snowman from the internet. Yeah.
These are some sad looking snowmen.
Right. Right. And we have pretty much, we have used a lot of variations where you could sometimes it's debatable whether it's a snowman or not, but at least it will cover all those cases where it is remotely looking like a snowman, right? So the data looks like that, the image data. And then if you look at the labels, sorry. So we have another thing for label. I don't know whether it's visible.
Yeah, I can see.
Okay. Yeah, you can see that this is the first one in this is the object ID. And here the object ID is basically 0. We are only using one object, but you could train it for multiple objects. So this is an object ID, and these are coordinates, basically x divided by the width, y divided by the width, and then you have, width and the width and height. And this width is the width of the bounding box divided by the width of the image. Does that make sense?
Yes, it made so much sense that it knocked off your camera.
Great.
It was so logical that we got a black screen now.
I have no idea why it's doing this these days. Sometimes it.
Yeah, we'll figure it out one of these times.
All right. Am I back?
Yes, you are back.
Okay,
Welcome
great.
back.
So we'll have to check. There is a small chance that the coordinates that I just described is incorrect. I cannot remember it. If it is incorrect, then it would be central. So this could be the distance from the center of the image, center of the bounding box. So this could be the x and y coordinates, not of the top left, but the center of the bounding box. And the width and height would still be the same, right? So you could easily plot it and see for yourself, but I can't, unfortunately, remember this. Okay, so basically we download this zip file. And as you know that when you download the zip file, it extracts this into this folder, JPEG images and labels. Once it is all extracted, we need to put them in the format that YOLO v5 expects. So YOLO v5 expects all the data to be contained in one directory. So we will do snowman_data. We will create another one called images and another one called labels, right? And the label is basically files which contain not just the label, but also the coordinates of the bounding boxes, right? And if there are multiple, you just have multiple rows for every one. So now we create the training data and the validation set for each, these are directories for the training and validation set. And we simply basically take 80% of the data for training and 20% for validation. And if you look at this, split data function, this is what it is doing. It's basically splitting the data into, 90-10. We could have used 80-20 also, but here right now it is using 90-10. 90% of the data is used for training and the remaining is used for test. And it's just putting them in the right directory. So once that is done, it's copying the text file, the image and the text file in the train directory, copying the images and the text files in the train and validation directories, right? This should have been called validation, but so this is basically copying the image and text files into the validation directory. Okay, now once we are done with that, we need to specify a YAML file for the configuration of the network, the training parameters, etc. That we need to provide. So that YAML file, this is our file that we are going to write, snowman.yaml. And it says that the path is snowman data. This is the directory inside which we put all the data. The training images are inside images/train. The validation images are under images/validate. And test, it's a small demo application. We have not put a test set. But typically, if you're doing, industrial grade training, you would have 60% of the data for training, 20% set aside for validation, and the test set on which you report accuracy, it is completely separate. 20% is left for that. And after you have done training, you have optimized the model, etc., the test set is only used for reporting accuracy. The validation set is used to see how well your model is training.
This is a place where I think people that are new to model training get kind of caught up, where they don't necessarily know that you have to keep them exclusive. And so, they get these great results, but it's because they're testing it on their inputs. It doesn't really work.
Right. Let me give you a quick idea of what needs to be done. The training set is the set on which your model is going to train. But once you have trained, you don't know. It's going to work very well on that training set because it has seen everything on the training set, right? And if you have not trained the model well, it will not do well on the validation set. When you test it on the validation set, it's not going to do well. And the analogy I like to use is that you must have seen people in your high school who would memorize the answers to questions, right? And if the teacher gave the same questions in the test, they would nail it. They would do very well. But if the questions were changed, and they would not be able to perform as well. So they have memorized, not really learned the concept. Same thing happens with neural network because they have so many parameters. If you let it, it's going to memorize everything. It is going to nail, the training error would be 0. And the validation error is where you will catch the problem that, oh, it's not actually performing on data it was not trained on. So the validation error would be high. Now, suppose you train it well and the validation error is also low and your training error is also low. Why do you need a test set? The test set is required because you change many parameters, etc., to find the parameters for training that work best on the validation set. So even though the network, even though your training process has never directly seen the validation set, the fact that you're using it to change the parameters indirectly biases your data. So your validation, you may think that, oh, I have never shown it to the network, but you have in the sense, right? You are the person who is in between adding this bias. So typically what happens is that you would get very low training error if you have trained the network well, a slightly higher validation error. The curves should still look about the same, but it would be slightly higher than the training error. And the test error would be even higher than the validation error. So that's very typical. So, and you don't touch the test set ever, you just use it for reporting the final accuracy. Otherwise, if you keep doing this again and again, you will, that becomes the validation set. So something to keep in mind. Okay, now what's there in the YAML? We have, put the paths in. We also have the number of classes, which is 1 here, and the names of the classes, which is Snowman here. But there are many, many different parameters that we can use. And here, if you go to the GitHub repository, they have this hyperparameter hyp.scratch.yaml file. If you look at that, it will show you all the hyperparameters that you can tune. And there are many of them. We don't have the time to go over those in this webinar. But one thing that I could have easily chosen to do is data set augmentation. And in this specific case, the kind of augmentation that would have benefited is flip left, right. So if you have a picture of a snowman and the mirror image of that picture is also a valid snowman, you could plausibly say, so you have doubled the size of the data set by simply flipping the image. Similarly, you can add some, some image transformations, some photometric transformations to the image by changing the hue, saturation, brightness, etc. And I actually removed some of these from my file because so I removed dataset augmentation from this notebook because I was doing it at the very last moment. I was setting up weights and biases. And I removed that because I wanted it to train faster right before the webinar. But typically you would use some kind of data augmentation, at least do flip left, right, do some kind of, gamma correction, etc. And this is all experimentation. Nobody knows what kind of augmentation would work well. You should just be careful that don't use augmentation that is not real. For example, recently, one of my teammates, they were doing some work on chest X-ray. If you look at all chest X-ray, notebooks, people where they are working on chest X-ray, they would use this augmentation where they would flip the image. But I I personally think that that's not a good thing to do at all. The reason is that if you look at the chest X-ray, you will see a heart. You can actually see your heart in those chest X-rays, and the heart is not symmetric. It is actually slightly tilted to one side. And if you look at the X-ray, and suppose you're trying to detect pneumonia, pneumonia would show up as white regions in the X-ray, and the heart is also a white region in the X-ray, right? And you will never get an X-ray where the heart is tilted. I mean, almost never get an X-ray when the heart is tilted the other way. So why put that as an augmentation when that data is not real? So I personally would not put
more data is not necessarily better in every case, and this
right.
is a good example of that.
Right. So I would personally not put that kind of stuff, or I would at least experiment, be mindful of these kinds of augmentation, because you may end up biasing your data and not getting good results. Okay. So yeah, so that was the YAML file. And then you can choose which model you're going to use. There are a bunch of models here. YOLO, YOLO V5, one, this is large, nano, small, extra large, medium, and small, right? You can choose one of them. This is the one that you're going to optimize. And then this is code for setting up some, train and test directories. Requirements file, we are doing it. And then this is the beauty of YOLO V5. They have provided a very nice interface to train the network. So all you have to do is run the train.py script with the image size, the batch size, what is the number of images in one batch, the number of epochs, which we had already set to 30, where is the data, and what is the starting weight, right? What weights do you need to start? Like we had said before, that here we are using the medium YOLO V5 as the starting model. After that, we are freezing most of the layers. Look at, we are freezing 20 layers here. And the reason is that, we have only limited amount of data. I cannot remember how much, but maybe 1,000 images. 1,000 images is not enough to train such a big network. So what we do is we freeze most of the layers and only fine tune on the last few layers. And then we run this, run this. So if you're planning to retrain the entire model, not just fine tune the last few layers, you should choose a much smaller model. Otherwise, if you use a bigger model and your data set size is small, let's say in the 1,000, then you should just freeze most of the layers. So that's a good rule of thumb. And yeah, so you run this training script, and it will run through it, finish all the epochs, etc. I'm just going over it slightly fast, but then you can, once you get the model, you can do the prediction on this thing, and you can see this example. For example, there were many small snowmen there, which it detected. So it's doing a pretty reasonable job of detecting snowman, and you can run it on.
You even got that upside down one.
Which one? Right. If you want to detect, the other thing is that if you really want to detect upside down or the sideways also, all you have to do is add that in the data augmentation, and it will have no problem detecting that.
Yeah, an example of good data augmentation here would be to flip the images and whatnot. Lost your camera again there.
All right, so now if you go back, once this training is complete, or actually not even complete, when the training is going on, you can actually go back to your weights and biases login, and it will show up. Yeah, so yeah, all your results will show up like this. You can see the confusion matrix, you can see the precision and recall curves, how they are going. You can also look at the training loss. So this thing is very important, that the training loss should be of the same the same rough order of magnitude for the validation loss. If you see that the validation loss is pretty pretty large, then you know that it is overfitting and it's not working properly. And finally, there is some place here where you can also download the model. I cannot remember it right now, but there is a place where you can actually download your model as well. So you can go to projects, and this is the YOLO V5 I ran just an hour back, right before the webinar. And that's why I was in a hurry to finish the training.
Just-in-time engineering.
Right. So that's pretty much it. I know that we went through the training process pretty quickly, but go through the notebook, and you will see that it is a pretty straightforward way. It is pretty straightforward to train an object detector from scratch using YOLO V5. You can try with your own objects. You can collect your own data and do it also. And if you want to learn deep theoretical things as well as hands-on practical experience, you should join one of our courses. We have 2 courses in deep learning now, deep learning with TensorFlow and Keras, which the Kickstarter campaign is going to happen on February 14th. And the other one, which is already present, is deep learning with PyTorch, which we have. It's a course that you can buy right now, or maybe actually wait until the Kickstarter campaign, and you may be able to get it for a discounted price. Some people may be interested in knowing, should they learn PyTorch first or TensorFlow and Keras? And the funny thing is that they are all converging to the same. Both of them are really good. Personally, when I started, I liked PyTorch initially slightly better, but they are all looking about the same now. And Keras is a very powerful library on top of TensorFlow that allows you to do many things very simply. So you don't have that learning curve anymore. The good thing about TensorFlow and Keras is that it is more industrial. It is widely used in the industry. The deployment tools are better. So if you use that, you're closer to deployment in some sense. And you should take these things with a grain of salt. I like to say the fact is that both these are pretty much the same now. It's not like you're going to hit a roadblock or something using any of these. You train a model using PyTorch, you will be able to deploy it anywhere. You train a model using TensorFlow and Keras, you'll be able to deploy it anywhere. So yeah, it's just a matter of taste and flavor, slightly different tools.
Yeah, personal preference and if what works best with your workflow.
Yeah. So we are ready to take questions.
Yeah, we got a couple of questions here. Alexander would like to know, does the model in your example only detect snowman, or can it be generalized to other objects?
It can be generalized to any object as long as you put it in the training set.
Right.
Yeah. So you put it, in our training data, we had the class number, which was 0. You could have multiple 1, 2, 3, 4, all the way, I think, to 9,000. You can have a lot of classes.
Word. Richard would like to know, what's the status of using YOLO V5 with OAK-D or OAK-D Lite?
I don't know, unfortunately. It's embarrassing. I don't know for sure.
Yeah, I don't actually know either. A great way to find out would be to look on modelplace.ai.
But I know that the nano version is just 2.5 megabytes. That should run blazingly fast. And as I said, that this is a PyTorch model. You convert it to convert it using this OpenVINO tools to OpenVINO format, and it should run.
Great. Michael has a question about almost, I'd say this a little more philosophical. Should you have non-class matching images in your training set to have, to train on not having a box, right?
I don't. So I
like,
don't
do we in our Snowman training set, do we want to have things that aren't snowmen in there where there's no images
implicit.
of snowmen?
That's implicit. Anything that. So you have to be very careful when you're training these object detectors, you have to be very careful to mark all the boxes, right? So for example, you're building a car detector. Sometimes what happens is people say that, oh, I'll just mark 4 cars out of 5. That should be enough because I have marked enough cars. But that is a very dangerous thing to do, because there is an implicit, it actually picks the other regions of the image as background, right? So it actually thinks that the car that you have missed, it could be background, so it can confuse it. So whenever you train an object detector, make sure that all the cars are marked properly.
That makes sense.
Yep.
We've got another question here about the data set. Valentina would like to know, will this work with different sized images? I know some of these things you need the training images to be exactly the same pixel dimensions and whatnot. Is that the case here?
Yeah. So what you do is basically you convert, any image can be converted into a fixed size. You could resize the image, stretch it in both dimensions to make it that dimension. You could crop from the middle. You could add padding. So you could use a combination of these: resize, padding, cropping, to make it the right size. And yes, there will be a loss of resolution sometimes, but that's always true, that you could lose some information. Small cars. So if you have small cars in a very large image, then you may want to do tile. You may not want to shrink the entire image, but take tiles from the image and do some post-processing to figure out, small objects.
Great. That makes sense. Henry would like to know, are we going to post these slides anywhere? Are you going to share these slides in the collab? Those will go on our YouTube channel at
it will go in the YouTube channel
/C/OpenCVAI.
Right. So by Monday, we post this thing by Monday, and in the description, you will see the slides as well as the collab notebook.
And the best way to be notified when that goes live is to follow us on YouTube and join the mailing list at opencv.org/subscribe. More questions. I think we got time for one more here. About how long did it take to annotate the training data for this project?
That's a very good question. The question is very good because it depends on how you are annotating, right? 1,000 images annotation is not, it's not a lot. So you can easily annotate, 1,000 images in a couple of hours. No, not maybe a couple hours, maybe 3 hours, right? It's not a lot. People think that annotation takes, object detection annotation doesn't take long. But let's say you are doing 10,000 images, 20,000 images. What you should do is pick one of these, commercial tools. I don't know, Super Annotate, RoboFlow. They all have, so what you could do is you could annotate 1,000 images and then train a model very quickly, and then do the annotation using that model. So most of the time you'll get it right, the annotation, and only a few times when it is wrong, you have to go and fix it. So you can actually, using some of these commercial tools, you can do the annotation really fast. Similarly with video annotation, there are so many frames in a video, when you can actually predict the motion of the object, and it will help you do annotation very quickly as well.
Great. Thanks for that. Yeah, I mean, we're 12 past the hour. We've still got a big announcement here. You want to unshare your screen for our big tease?
Yes.
So yeah, why don't you tell them what we're working on, Satya?
Yeah, so we are working on an AI game show. So the idea is that we will have, like any other game show, like Who Wants to Be a Millionaire. This will be a game show where we'll invite some guests, ask them questions about AI. It would be both educational, funny, and it will be like a game show. So we are still, deciding when exactly the game show will go live, but sometime in March. So March 17th is the tentative date right now.
That's right. And it'll be broadcast live here on OpenCV weekly webinar as well.
Yeah. So it's a new concept. We'll see how that goes. We are pretty excited about that. Initially, the people who will be chosen for the game show will be, some influential people in the community, in the AI community. But for this game show may happen if it is successful, right? We may actually do it more often, quarterly or so. And in that case, we may also invite people from the community, do a small test so that people from the community can come and be part of this game show.
That's right.
So,
yeah, we're really looking forward to the first episode here. Like you said, it'll be sometime in March, and it's going to be a whole lot of fun.
Yes. So yeah, if you join our newsletter, opencv.org/subscribe, we'll keep you posted on these.
We sure will. And with that, do you want to take us home, Satya?
Yeah, thank you so much for joining. This is really incredible that people from all around the world show up every week, and we have such a good gathering, and we get to share something that we have learned. Thank you so much, Phil. That's all I have to say. And please head over to opencv.org/Kickstarter to learn. We don't have much information about the Kickstarter campaign, but hit the notify button, which will notify you when it goes live. We have some very special deal on the very first day, which is Valentine's Day. Mm-hmm. So
yeah, you definitely want to hit that notify button on Kickstarter so you make sure you get the good deal.
Yes.
Next week, we will be probably showing some of the awesome projects for the OpenCV Spatial AI Contest, where people are combining AI with Lego. You can see some of that work on Twitter and Facebook, etc., with the hashtag OakDLightContest. Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision from the experts at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.